disk of intersecting screws, because the transmission ratio, by the way, is the same. It's 50 microns per degree for both of them. So let's do a disk that has a pitch of 50 microns per degree, essentially, right? So that transmission ratio that you want, 50 microns per degree of rotation. That's a pitch. So you get screws of all that same pitch, okay? And let's design something that achieves that, okay? Well, you look here. Here it is in the 2DOF column. Here's its constraint space. Okay, there's two things in here. 6 minus 2 is 4. You'd pick 4 non-redundant constraints. You could pick 2 from 2 of the circular hyperbolae, but why not pick 1 from the center one and then 3 from one of the circular hyperboloids? That's because the most they can hold is 3, right? And so let's do that. That's the easier one. So we're going to pick 3 from this one and 1 from this one. And that's what we're going to do. We're going to take the 3 on the outside that lie within this circular hyperboloid. And you can make those 3 just by this and bolting on the sides. Make sure that, of course, they're the same angle but the same distance away. And then, a third one right down the center made from this, okay? So those are 2 unique parts. Make 3 of one and 1 of the other, bolted on there. And you'd find if you ground this achieves this disk of screws, which is pretty tough to visualize, but you can think of it, if I ground this and I push, or if I pull along this axis, push or pull, it will rotate with that coupled pitch. And then if I push along this axis, it'll rotate along that. And really, if I push along any of those axes, it will translate as it rotates around it, okay, with the same pitch. Okay, but how is this useful for what we're designing? Well, what you can do is, first of all, make sure you set these angles and distances so that it equals the pitch that you want, which is the transmission ratio 50 microns per degree. Make sure you convert to radians, though, because that's going to throw you off. Okay, but make sure you tune all this correctly. Okay, and now what you do is, instead of grounding this, let's allow this to just translate in like a disk. So we're going to add a bearing onto that only allows translation there. Then we're going to add a bearing on that, some kind of flexure bearings that force these to only rotate around those. So that every time you translate one of these, this one's going to rotate with that transmission. If you translate one of these, the parallel one's going to rotate with that transmission. Okay? And P will be our approximate transmission ratio. Okay, or at least get us in the ballpark, and then we can tune it later. Elastomechanically. So this is a great flexure. It's very famous that achieves just 2 pure translations. Okay, so you can see it's kind of like 4 serial limbs, in parallel. So it's a hybrid system, and we'll just slap that. It achieves that freedom space. We'll slap that on the front face there to force it and ground it here. So we force this to only translate, and then we're going to actually slap some flexures on the back here to force only these rotations in the disk. And by the way, you wouldn't want to just add all the constraints that would achieve rotation there. There's constraint through this structure, through that also constrains this. So it turns out you only need 2 wires back there in addition to the constraints all through the rest of it to achieve that disk. And so now you've got this constraint so that if you rotate this back stage about anything that's guided to only rotate in the disk, you're going to get an output transmission of the output stage with the transmission ratio you wanted. But we have a problem, because if, say, we rotate this, right, sure, we'll get the translation here that we wanted with the transmission ratio, but this guy will move over. And that's no good. Like if we just stuck the handles on there and there, when we rotate that one, this handle's going to like rock over, and that's very unpleasant. If you want to rotate this one, you don't want the other one to be moving. You want to just have the handles stay put and independently rotate them. So what we need to do is put a handle floating away from here and attach it to ground here. This is all ground. And put these intersecting flexure blades that, of course, over-constrain, but they will, they lie in these intersecting planes, and so they achieve this rotation. So at least those are flexure bearings that will constrain that so it can't move in any way but rotate. And then here's the magic. We're going to add this. This is the decoupling flexure here that, if you think of this as ground and that as stage, it lies on these intersecting planes, so it allows a rotation there. So what that does is if I rotate this, it will be absorbed by the instant center of these two. These guys will just deform freely, and this one won't move at all. And yet it'll pass that through and get what you want. But the cool thing is if I rotate this one, these will stiffly pass this rotation through, and it'll cause this to rotate. So this is great because when you rotate this, nothing happens here, but when you rotate this, it'll still cause this to rotate. And so if you want to decouple the other one, so it'll pass this through to that, is what I showed there. If you want to do it to the other one, you can put this one up there and do the same thing. Okay, so now at this point we're done. If we, let's put a thing back here to just make it even more rigid, because you don't want the grounds to be deforming when you think they're ground. Okay, and notice it's all made in planar pieces, and so that we can fabricate this. And you can see I'm rotating this, and this is translating with the transmission we want, but this is barely moving at all. And then so there you go. And then I can rotate this, and this is translating out with the transmission, but this is barely moving at all. Okay? And it looks much cleaner in reality. We built this on a water jet, put it together, and let's see if this is going to play. Okay. Let's see. Is this going to play? Uh-oh. Well, this is a really cool video, so we need to see this play. Hold on. Okay, let's see. Okay. I think I know what's going on here. Okay, so that should work now. All right. Okay, so here we are. Okay, so you can see our hands pushed there. It causes this output thing as a dial indicator to move, and this one didn't move at all. Now you push this one moves. That one doesn't move at all. Okay, so we have this very nicely decoupled where you just apply pressure on either of those handles, and you can see you can very repeatably control things on dial gauges that are moving very small amounts, okay, and in a completely decoupled way. Here, I'll show it one more time. Okay, so watch this. This one's moving, that one's not moving at all. Okay, now we do this one, we touch this part of the structure, that one moves, that one's not moving at all. Okay, and here it's just one big monolithic structure all bolted together. So pretty cool. Okay, and we actually did some rigorous actuation and testing and got measurements on it. You can see here side handle input rotation to output stage translation, and you can see this one shows vertical displacement was not happening, and the horizontal one was too. So you can see how decoupled they were. Okay, and that's experimental data. Okay, so it worked beautifully, and you can do all sorts of neat things. So now here what we have is a transmission-based microstructure, so or architected material. So imagine you had these little unit cells that connected, say there's some weird design inside this box, but they had these tabs that stuck out of all six sides, and they connected at this tab, so you can see there's space in between them. And then these are all tiny within a giant lattice. So say these are so small you can't even see them with the naked eye, and you just have this big chunk of material that looks like a homogeneous material. Well, if you were able to design these with crazy transmissions, so if I push there, this gets a rotation, this gets a translation, you could get this whole material to change with weird shapes. Okay, one of the more useful ones is if you push on the tabs, you have all the other tabs pull in. And that would get a negative Poisson ratio. That would be very strange, because most materials, when you crunch them, they bulge out. It'd be really crazy if you got a material that had a positive Poisson ratio, but you architect it like this, so that even though the bulk material it's made of has a positive Poisson ratio, once you crunch it, everything pulls in and it behaves as a negative Poisson ratio. Okay, so you can kind of see how this design could work. It's admittedly not a good design. It's very complex. It doesn't have planes of symmetry. It wouldn't be isotropic. There's all sorts of issues. But it shows what I've taught you nicely. And there are much cleaner designs that are much more symmetric that can achieve this. But this is a nice thing for our discussion here in this lecture, that you can see here, if these are grounded, when you push this in, you have this rotating thing that turns these translations into other translations. And then here you can see if this has a bearing that only rotates, and this guy on the top has a bearing that only translates, this screw will, when it can rotate and this can only translate, will pull this in. Okay, and we've seen that before. And if these are really too hard to 3D print, you can use these other flexures and 3D print them that we've seen before. Okay, and of course such materials would need to be 3D printed, and they're to the point where you can on tiny scales, like tens of nanometer size features. You can print them and get some really neat materials. Okay, so fixing under constraint using transmission is the next topic. So you might recall that I introduced this in the last lecture here, where say you have this grounded, and you just didn't have this part. This would cause a translation. Okay. Then if you attach this on there and you ground that, this would be a translation. So this is a serial system with two redundant degrees of freedom, and so it's under constrained, meaning if I hold this fixed with respect to that, this can bob around uncontrolled. And they may go in opposite directions, which would be really bad. But the good thing about this is that in a fairly compact space, you can achieve twice the range with this than you could without the intermediate body, because this goes 1 and this goes 2, because it can go as much as this and then twice as much if these are the same lengths, right? And so, but that's only going to happen if this goes, if this is forced to go 2 to 1. Because if you actually push this, this will try and snap back, and it won't be a 2 to 1 ratio. There's nothing forcing this to be 2 to 1. And so as a consequence, if you force this to go 1 and this to go 2, they will cancel out the arcing parasitic motions, and you'll be good, and this will go twice as far, right? But if you actually push this will try and snap back because of the stiffness, and it won't achieve a 2 to 1 ratio, right? This will be more than that. It won't do it, and you'll still get some parasitic error. So one way to fix this is to use the slave-master kind of thing, where this guy is the slave and this guy's the master that's kind of driving it, and this rotates here, and what you do is you now have, by adding this, have gotten rid of under constraint. Right? So if you hold this final stage fixed with respect to ground, everything, including the new body, is locked up. These guys can't go in opposite directions, so that's great. We fixed the under constraint. And because these distances are the same here, when you rotate it, this guy will move half the distance as that, and you'll fix the parasitic error. Problem is you added another huge mass, and it's not symmetric, and it's really ugly, and the grounds are all apart, and so it's not good. Okay, so maybe there's a better way to do this. Okay, and let me re-step you through it. So here's a parallel system that translates, okay, but it actually arcs a little bit. Okay, well, we can have the exact same size mechanism, keep it symmetric, and get twice the range if we make it serial and nest it. We have these be the same length. We go from these two grounds down to the intermediate stage and back up to the stage. And so in the same footprint, you can get twice the range, and as long as this goes the 2 to 1 ratio I told you about, you'll cancel out the parasitic errors, and this will be a pure straight line. Okay. Problem is that this is under constraint. There's a redundant degree of freedom. So if you fix, one, they can go in opposite directions, which is bad. And two, if you fix the stage fixed with respect to the ground, this guy can vibrate not unconstrained. And there's nothing forcing these guys to move the 2 to 1 ratio. So if you push this guy will try and snap back, and it won't be 2 to 1, and there will be parasitics on this. Okay, so how do you fix the under constraint and fix the parasitic error? Well, you can add an under constraint eliminator. Okay, is what it's called. And this is, of course, all these designs I'm showing you are interconnected hybrid. And basically you add another Also symmetric, rigid body, hollow out the mass, cut the triangle out to hollow out the mass. So this is supposed to be like a rigid truss. It's just a big rigid body. We added this flexure and these two flexures and this flexure here. Okay, what this does is, again, it doesn't increase the footprint of the system. It maintains the symmetry through the system. But what it does is it constrains, it gets rid of the under constraint. So if you held this stage fixed, this final stage you care about fixed with respect to the ground, everything would be locked up. These guys are not allowed to go in opposite directions, and you're not really compromising the range much at all, as long as you make these compliant enough, right? So you can still get twice the range. But the cool thing, in addition, is it forces the 2-to-1 ratio. And the reason is, if you think about it, here's the ground. Here you have an instant center here, so this triangle is forced to rotate around this point. Okay? And so if you think about it, if the triangle is forced to rotate around this point, 2h times the amount that it rotates is the translation there. And then down here, 1h times the amount it rotates is the translation there. And these flexures are just to kind of absorb the rotation there. So you can see this one is forced to translate approximately h theta, and this is forced to translate approximately 2h theta. So it's a 2-to-1 ratio. And it gets rid of parasitic error. So it fixes everything. Okay? This is what it would look like in the translational version. There's a rotational analog here. And by the way, this is just one of possible under-constraint eliminators. But so say you have a rotational joint, a revolute joint that rotates at the instant center of these things. Okay. Again, it's got whatever size it is. It's symmetric. But the problem is that it can't rotate terribly far without yielding. And the axis of this rotation, which is right here where you see the red dot, over large deformations will actually drift over to the right as it deforms larger and larger amounts, so it'll have a parasitic error. Okay? So if we add a stage inside and nest it back and forth, first of all, it's still the same size, it's still symmetric about the center, and now we can double the range, right? This guy, this guy can now move, and this guy can move rotate as far as that, but also rotate twice as much. Okay, so we doubled the range. And the cool thing is, not only do we double the range in the same footprint, but because these are opposing, the drift that would be caused by these two cancels out the drift that would be caused by these two, so the axis of rotation stays put as long as this rotates twice as much as this one, which wouldn't occur in this design, because if you rotate it, this will try and snap back, and they'll still be a little parasitic. But it is better than the last design, in that you can go way further with a little bit less parasitic, but the problem is it's heavily under-constrained, so that if you hold this fixed with respect to the ground, this guy will vibrate uncontrolled, and they can go in opposite directions, so it'd be a mess. So what it needs is an under-constrained eliminator. By adding this under-constrained eliminator, you don't increase the footprint, it's still symmetric about the axis, okay? And you can now get twice the range, just like you wanted, and yet, this guy is nothing's under constraint. If you hold this fixed with respect to the ground, this and this will be totally locked up, so that there'll be no lack of control if you're actuating this. So under constraint is gone, obviously. That's why it's called an under constraint eliminator. And the cool thing is this is forcing the 2-to-1 ratio, so there's no parasitic errors. Okay? And so check it out. As you rotate this body here, you can see this one will translate a... So notice this guy inside, here's the ground, here's parallel guys. This guy can only translate. As this guy translates the distance d, this moves a distance d, divided by that h is how much this body rotates, theta 1. But as this translates d, it's still translating d here. But if you divide that by 2h, you get this theta 2. So you can see this is half the rotation of that. And hopefully you can see how beautiful this is. For the translational version, all the bodies are translating, but this guy was rotating, the under constraint eliminator. Now for the rotational version, these guys are rotating, this guy's translating. So it just flips it inside out, basically, and does the exact same thing. Okay, so under-constraint eliminators are great. You can have the mechanism be the same size, you can double the range, you can eliminate any issues with under-constraint, so you can have your cake and eat it too, and you can get rid of parasitic errors and force things to be really nice. And so these are all interconnected hybrid systems and advantages of why you'd want to design something interconnected, even for precision flexure systems, in addition to metamaterials and stuff. So definitely take my next class, the follow-on to this flexure class. Okay, so those were two planar designs, but you can do this as complex as you want in 3D. So consider this design that is grounded down here and it achieves just a single rotation, okay, with a 3D thing. Well, you can double the range without increasing the footprint much at all by having this be ground, go down with these flexures and then go back up. And so in the same size, you can get twice the range and help get rid of some of the parasitic error. You know, in this case, as it rotates, it actually pulls down a little bit. It actually screws down. You don't want that, right? And so with this, as this guy rotates, it actually screws up a little bit, and this rotates, it screws down to the point where this doesn't move. But that's only if it's the 2-to-1 ratio, which this does not enforce. So still, same footprint size, twice the range capabilities, but there's still slight, it fixes parasitic error a little bit, but still slight parasitic error. But the problem is it's very under constrained. If you hold this fixed with respect to the ground, the stage, the intermediate body can now rotate uncontrolled. Okay, so what we need is an under constraint eliminator that's designed by fact with screws in here to tune all the transmissions to be just right, so that as this central intermediate body translates, these guys are forced to rotate 2-to-1 ratio. And with this, we didn't increase the footprint. Everything's still nice. If we fix the stage with respect to the ground, everything, including all the bodies, will be locked up. Nothing's under constrained, and it forces the 2-to-1 ratio, so there's no parasitic error. Okay, but that's just a single degree of freedom. What if we wanted a system that achieves multi degrees of freedom? So the translation there, and rotation there. Okay. Well, what we can do is and that all has parasitics and it yields quite quickly. But okay, so what we can do without increasing the footprint much at all is nest it in series. Put a ground here, go down here, and back up. Okay, that will get twice the range in this direction, and in that direction, and it'll help get rid of parasitic error. It won't perfectly, but it'll help get rid of it. But the problem is now it's going to be massively under constrained. If you hold this stage fixed with respect to that, this can vibrate in that direction, that direction, that direction. So it's under constrained in 3 directions, the intermediate body, so that's a mess. But if we add an under constraint eliminator, very cleverly and designed with fact, using interconnected hybrid theory, you can design this so again it's the same footprint, can move the same range, twice as long in this direction, and this direction, and it eliminates the under constraint. So if I hold the stage fixed with respect to that, nothing can move in any direction. It's all totally locked up, and it fixes the 2-to-1 ratio in all 3 directions, right? So this direction, this is forced to rotate twice as far as that. This is forced to translate twice as far as that. This is forced to translate twice as far as that. Okay? So it's pretty cool how complex fact can get and what you can design that no one could intuit or no other design theory could generate and achieve. Okay? And that uses transmissions to force. The whole reason it's in this transmission lecture is because we're designing under constraint eliminators are basically transmission mechanisms that force the 2-to-1 ratio to get rid of parasitic error. That's why it's in this lecture. Okay, so remember I told you, well, first of all, let's show you something a little confusing here. Okay, and then I'll tie this back into what I told you before. Okay, so say you've got a block that's grounded, you've got a block that's grounded here, and you've got this one-dimensional system. These 2 blocks are only allowed to move up and down. And you've got this idealized stiffness K and this idealized stiffness K2 and K3. You've got, say you want to drive the input here, some displacement. You've got a displacement actuator that you control the displacement. You have no idea what force is on it. And then you want to measure the displacement here and find out what the X output to X input is, the transmission ratio of that. Well, you could calculate that using simple spring mechanics that you learned from high school. Let's do it. It's a little tricky, I guess. If you think of it, if you move this, these two springs are essentially in series, right? So you can imagine this just totally gone. If I move this, we calculate the force in this spring, which is in series here, by taking this, right? We take K1, invert it, K2, invert it, add them together and invert it. That finds the equivalent stiffness of this spring, which is basically in series. And again, you could just shrink this to a dot and consider this one spring an effective spring, and here's what its stiffness would be. Okay, so you move this up some distance x input, times it by that stiffness, and that will tell you the force in this equivalent stiffness spring, which is, of course, things in series, they all have the same force in it, not the same displacement. So both these springs will have the same force in it, and it will be this force. So if you then, so that's the force, right? So if you then times this amount by the inverse of this stiffness here, okay, which is in other words, divide it by K. So this is basically a force here in both these springs, but we're looking at this spring. So the force in that spring up on top is this amount. If you then divide it by that stiffness as K, you get the displacement of that spring, which will be the X output. Okay, so hopefully you followed that logic. You do know this from high school or freshman year of college or whenever you learn this, but you still have to be clever with how you set it up. Okay. Okay, so then if you take the ratio of X output to X input, you get that the transmission is this. Okay, so that means if I move this some displacement here and times it by this amount, I will get, this, which is entirely dependent on these stiffnesses, I'll get the output transmission. Okay, so that's the transmission ratio. That's the geometric advantage, essentially. Okay? All right, but what if I swapped these so that this was the input and that was the output? Well, now I do all the exact same proof, except check it out. Instead of K1, it's K3 here, all inverted. So it's very different. And I mean, it kind of makes sense. Before, if this is the input and I force this with a displacement, it's as if the spring isn't even here. It's not a function of it at all. Whatever the spring is, I can just get rid of that spring. And I force a displacement here, and it wouldn't change the calculation of the output here. And the same thing now, if I force this to be the input and I displace it, it's totally independent of K1, but it's totally dependent on K2 and K3. So if K1 and K3 are dramatically different results, then whether I make this the input or this the input and the output's vice versa, it's going to be totally different. So if I drive this 1 centimeter and this moves, half a centimeter, and then I grab this, move this half a centimeter, this is not going to move 1 centimeter anymore. It's going to do something different, okay? Which is weird. You'd think they'd be different. Or that you think they'd be the same, but they're not. And if you think about it deeply, you can see that they're very different. This one has nothing to do with K1, this one has nothing to do with K3. Okay, but remember, in our one-dimensional idealized thing with scalar springs, we can apply the exact same things with our stiffness matrices from lecture 3. We can take stiffness matrices, 6 by 6 stiffness matrices that capture the stiffness of entire parallel modules. Either, it's a 6 by 6 stiffness matrix for an element, but these are all these things in red, or are in parallel, so you add them all together. So you can have, this is a twist wrench stiffness matrix for this parallel module, and then the one in black here, I show the flexures in black, or is this stiffness matrix. Then the screw in green is this stiffness matrix, okay? And hopefully you can see how this is configured the same way. Remember, we've grounded this on the outside like that, grounded this on the outside like that, and the one that connects this intermediate body is this one. Red ones are connecting it there. This one to this one, that's a green, and the ones from this one to this one are kind of black or dark gray, right? So just like we proved this is the case, okay, you can show that if you just take these matrices, the matrix math still works. It'll be the same thing except you plug the matrices in, and instead of X being the input, you take the twist, a twist input, okay, and then so get the twist output, okay. And so you just set the twist to be a pure rotation, times it by all this, and you know how to find these stiffness matrices, and you'll get the output, which you'll find to be a translation with a certain magnitude that's related to the magnitude of the rotational input. And you divide that rotational input magnitude, omega, by that V output, and that will be your transmission, your true transmission. So remember, I told you